away from you. At this point here, 0 is going perpendicular line of sight, and then it starts going away from you, negative. I'm sorry, I mentioned it.
So you end up knowing do you end up knowing the size of the orbit then?
Yes, exactly. Because you know the speed, you know the time.
Right.
So the spectrum shift can give you a velocity?
Bingo.
Okay.
This number over here is based upon how much the lines have shifted.
Okay.
So what you're seeing here is they'll start coming toward you, start going away, start coming toward you, start going away, and you plot it up. But the key is you only see the one star. There is no second spectrum because you can't see the planet. What makes this possible for the first time in history, 1995, is look at the scale. This is 100 meters per second motion. You're measuring a change in velocity which is on the order of less than 5 meters per second. So if I go from basically walking to running, I can see the difference with my telescope. For a star which is 50 light years away. Right? So this is why the technology changed the nature of finding planets. We can now do this this is 5 meters per second precision. They're now working down around 1 meter per second. So you can walk 1 meter per second, no problem whatsoever. They can measure that speed at a distance of 50 light years. Easy, right? So the key is I can measure, there's a planet here. Okay, wonderful. Problem.
Always a problem.
Always a problem. Always one more top of everything. Oh. The problem is, what kind of planets am I going to find? I want to see a speed change which is measurable. To have a speed change which is measurable, it has to be large. All right? What kind of planets are going to have large speed changes on the star as they go around them? The answer is, the planet has to be really close to the star and heavy. So when you go through and you try to find stars which have this kind of motion, you grotesquely, biasly select your sample to identify stars with really massive Jupiter-sized planets about the location of Mercury relative to the sun. Now, we don't have Jupiter-sized planets where Mercury is. We have terrestrial planets. So when you do this sample, you tend to pick out all the oddballs, the ones which are really heavy, very close to the star. They are not typical, and this takes a long time to do.
Does weight have any correlation with the possibility or not possibility of life form?
We'll talk about that at the end, I promise. We're getting there. Yeah.
Question.
Yeah, right.
You described like the simplified version of looking at
Yeah.
you know, on the normal plane.
Yeah.
How do you deal with the fact that a lot of times the motion would be whatever the sine of something
Yeah.
because it would be at
Tilting.
a tilt?
What would happen is you get the same plot, but the amplitude would get smaller.
But how do you know? How do you
You don't.
determine what the angle
You don't.
is and what the
You don't.
theoretical normal is?
And Marion, if you measure the mass, the answer you get is the lowest possible number.
All you
It could
know
be
is-
bigger.
All you know is there's something out there.
Something out there, but you can actually measure a mass. But the mass would be the lower bound. It's 3 Jupiter masses, but it could be 4, 5, or 6, depending upon the tilt. Okay? We got that, vaguely? A classic example, let's take it 90 degrees. I see no Doppler shift at all because all the motion's this way. I can't possibly do anything with that. All right? Understood? Okay, good. 3. The good one. It's always the last, the good one.
Goodness.
Here's the idea. It's called transit photometry. The picture you're going to see is going to show you what happens when a planet passes in front of a star. What you're measuring here is the brightness. You're sitting out there and you measure this system, how bright it appears to you. If nothing changes, nothing happens, fine. But now because this planet's passed in front of the star, it's blocking off some area of the star behind it. So the total brightness you count goes down. It's an eclipse
You're measuring the brightness of that.
of everything in that fine field of view. And the planet's included in your counts. All right? So I can tell there's a planet here because that planet went across the face of the star. The brightness, when it starts to go across, drops. It stays that way until it starts to emerge at the other side. So all I have to do is measure the brightness of all these stars and see which ones show an eclipse. Okay? Problem. Always a problem. It works well, except for a problem if you're trying to identify planets. First problem is the drop in brightness depends upon how big the area of that black planet is relative to the area of the star. An example, if you're sitting out there on some distant planet looking back at the solar system, and the Earth goes in front of the sun, which it does all the time. When it goes in front of the sun, how much does the brightness of the sun drop? And again, it goes as the area of the planet to the area of the sun, which means in the case of the brightness of the sun, it drops by 1/100th of 1%, which is small. Okay?
No kidding.
When you do photometry and stellar astronomy, a good number is 1%. A great number to measure in terms of precision is 0.5%. This is telling you you need 1/100th of a percent to see the drop in brightness, to know it's there. Second problem. How likely is it you'll actually get an eclipse? Again, to get an eclipse, you got to be edge on. Planet, here's the plane, the planet goes like this, and you're lined up straight on, edge on with the planet. It turns out that the probability depends upon how far away the planet is from the star. The further away it is, the smaller the probability. The closer it is, the higher the probability. But as an example, if all the stars in the sky were the sun and the Earth, and I picked a random sample, how many stars will actually show me an eclipse? And the answer turns out to be about 0.5%. All right? Not too bad, but keep in mind, most of the planets are likely to be further away than that. 1 AU, the Earth-Sun distance, is a small volume. All right? But it's still, it means it's workable.
You know that number because you're inferring the eclipse of the sun or Earth?
Yeah, exactly,
Okay.
exactly. Okay, so what do? Well, if you're slow, you take your telescope and you point at one star and you observe it. Doom, doom, doom. Every night, non-stop, for 5 years. In the hope that maybe by pure dumb luck, this one star will be the one that's lined up exactly edge on with a planet the right size to curl across your field of view to show an eclipse.
Amazing.
At night.
At night, yeah, well, we're stuck with that, unfortunately.
We're stuck with that.
The other thing you can do, though, is do lots of stars. This may be only 0.5%, but it means if I do 200 stars, I got one chance of finding a planet around one of those stars.
Right.
So you want to do as many stars as you possibly can for as long as you possibly can, so you'll be lucky enough to catch an eclipse. And here's where we finally get to the talk. No. Only another 2 hours to go. All right. Here's Kepler. Kepler was a spacecraft launched in 2009. It was designed to do one thing and one thing only: measure the brightnesses of stars. The satellite has a mirror which is 1.4 meters across. It's relatively modest size. Ground-based telescopes now are 8 to 10 meters. Space-based telescopes are typically about 1 meter because it's expensive to launch the satellites. There's a thing up here called a Schmidt corrector. Anybody knows anything about telescopes? Anytime you have a Schmidt corrector in your telescope, what you're trying to do is make sure the image across a wide field of view looks good. Most telescopes, if you point at the sky, they'll give you a nice area of the sky which is clear and sharp and in focus. But if you go outside that limited range, it suddenly gets out of focus and pointy. The data goes bad. The Schmidt corrector tells you you want a wide field camera, which looks at lots of objects and gives you good data for all of them, not just the one near the center of the field. How big a field are we talking about? Oh, it doesn't orbit the Earth too. It orbits the sun. It orbits at the same distance as the Earth from the sun, but it's not orbiting the Earth. It's back here behind the Earth, so it trails behind the Earth. That means we can use it 24 hours a day. The problem, for example, with the Hubble Space Telescope is it orbits the Earth, so every time it comes between the Earth and the sun, you've got to turn it off.
Ah,
So every 90 minutes, you stop observing because the sun's in the way. All right? This means you can point the telescope and never have to worry about the sun. All right, here we go. This telescope has 42 CCD cameras on it. Lined up like this. These are two CCDs, the same thing you have in your telephone. All right? You make a picture with it, except these are a hell of a lot more expensive and much better quality. But the reason why there are 42 of them is the area of the sky covered like this is real. This is the constellation Cygnus. This is 10 degrees by 10 degrees. 10 degrees across is 20 full moons lined up. So when you take a picture with this camera, you get an area of the sky which is 20 full moons this way and 20 full moons this way. It's 100 square degrees. That's huge. Most telescopes have a degree field of about 1/4 of a degree by 1/4 of a degree. So this is designed to give you a huge area of the sky all at the same time. All right? So what does it do? See that spot in the sky where it's positioned here? It points there every hour, every day, every minute for 5 years. It was designed to do nothing but look at that area of the sky for 5 continuous years. And it takes an image every 3 seconds. And you measure the brightness of every star in that field of view every 3 seconds for 5 years. And then you construct light curves. Here's a star. How bright was it then? For 5 years. And see if anything changes.
Why that particular area? What was the decision?
It was picked because A, there were lots of stars, but B, there were also a few star clusters in this field of view which cover a wide range in age. A young one, an intermediate old one, which is about 3 billion years old, and a really old one, which is about 10 billion years old. So in addition to seeing the individual stars, like random stars in the field, you can actually study individual clusters here. How many stars are we talking about? You're measuring the brightness of 160,000 stars. Not 5, not 200, 160,000, non-stop for 5 years, every 3 seconds. That's a lot of data. But the beauty of it is, because you have so much data, you can get really good precision photometry. If you can change the brightness by less than 100%, I can measure it. All right, example, I look at a 12th magnitude star. If I use this telescope for only half an hour, my precision is down to 5,000ths of 1%. So it's great. If I do it for 5 years, I get tons of data with really high precision. Okay? Now, when this first got launched, I'm a photometrist. I tend to doubt things like this because I've worked in photometry. I know how difficult it is to get really good stuff. And this has to be really, really good stuff. The thing that convinced me was this one. They started releasing the data after the first few months. And they showed this plot. This is a light curve. Again, these are just individual measurements of brightness over time. This is ground-based data. This is a star you actually measure with a small telescope from the ground. And what you see is lots of scatter, but then it drops. Here's your eclipse. It goes back up again. This is the same star observed by Kepler. That's not a straight line. The dots are just so small you can't see the scatter inside the dots. It's the same overall curve, but seen from Kepler versus the ground.
Oh my goodness.
Let's blow it up. Let's expand the scale by a factor of about 10. Here's your light curve. Note the scale over here. This is 1 for total brightness. It drops by 0.6 of 1%, and that's the brightness drop. So you can see, here's the star, it drops, you get an eclipse. You look carefully, there's a second one over here. Because what happens is when the planet goes behind the star, you lose part of the brightness. The planet's not that bright, but it's enough to cause a change in the total brightness of what you observe. So let's take this plot now and blow it up again by another factor of 10. And this is what got me when it first came out. You blow this scale up so it's 10 times larger, and you still see the same eclipse. But you look carefully, this is 1.001, this is 0.9998, so it's a change of 0.02%. Notice this, it's not flat.
No.
It's dropping down, then the eclipse, then it goes back up, second eclipse, it goes back down again. The question was, why is it doing this? Why am I getting a brightness change when there's no eclipse going on? Here's why. And this is amazing, absolutely amazing. We said that you see a planet because of reflected light. This is what you're seeing, the planet's there because of reflected light. Think about the moon. During a month, what does the moon do as it goes around the Earth as seen by somebody in the Earth? The answer is the moon goes through phases because you're seeing different angles at which the moon is being illuminated by the sun. The planet's doing the same thing. As it goes around the star, it gets illuminated by a different amount depending upon the angle at which you look. Now I can show you that. Go. You're seeing the phases of the planet. Yeah, that's amazing.
That is amazing.
Here we have it. This is what it looks like to begin with. Again, this is your planet going around the star. Now they're going to show you the planet blown up. Look at it. It's going through phases. All right? It comes back out. It's starting to brighten again now. So you're not only changing the brightness of the star, the actual fraction of the planet you can see is changing because of the phases as it goes around the star. And I can measure that, which is extraordinary. All right, move on. All right, here we go.
Is that extraordinary because it's more confirming of the presence of a planet?
Yes,
Okay.
because if it were a star, that would not happen.
Right.
Two stars would have their own internal illumination, therefore the star brightness wouldn't change.
Right.
This tells you it's got to be a planet.
Right.
Okay.
Right.
But the precision is also incredible. This is not the best in terms of precision. You can go better, another factor of 10 beyond this in terms of accuracy. So this is just the first 3 months of data came out and it showed this for one star. So since then, there have been tons of analyses of the data from Kepler. Kepler failed, unfortunately, because of problems with the fly. When you point the telescope, you've got to have to change direction all the time. And you do that by using a series of flywheels. The problem is the flywheels are mechanical. If the flywheels fail, I can't point the telescope anymore. So in 2012, 2 of the flywheels out of the 4 failed, and they couldn't point it any longer directly at the Kepler field. They figured out a way to use it anyway. They have now, as the telescope goes around the sky relative to the sun, they have a little device on the telescope, which is there for another reason, which always points to the sun. So they have a third direction because the light source always tells you where the sun is, and they use the other 2 flywheels to point the telescope. So it's being used, but not on the same field anymore. Brilliant people who did this. Anyway, so here we go. Summary. What's out there? As of May 10th, 2016, this gets updated every day. This is the last plot I could find. Here are the number of planets found every year prior to 2009. These are all being found using radial velocities. The first technique I showed you, measuring the speeds as they go around each other. These are radial velocity discoveries. There's one here in 1995, the first one. There's about 30 or 40, 50, 75. It's growing.
Those are planets within that field?
No, these are planets discovered by a totally different technique. These are ground-based observations using spectroscopy to measure velocities. Okay?
Gotcha.
And the numbers are increasing because as you wait longer, you get a better chance of seeing the velocity change.
More precise.
Bingo. Now we launch Kepler. And what does the data look like now?
Oh my God.
Kepler is all the white stuff and the yellow stuff. So you're adding about 50, 75 planets a year. Kepler goes up and boom! You're adding thousands of planets on an annual basis. So this is why Kepler is so important. It takes a sample from a few hundred up to a few thousand outside the solar system. How many are we talking about total? The last numbers as of yesterday were 2,925 found by radial velocities in transit. That's Kepler and ground-based radial velocities. Another 25 were found through imaging. The kind of stuff I showed you with the red star and the blue star.
Oh, yeah.
You can still do that. It's just very not easy to do. Then there's a whole 2,500 planets identified by Kepler as being probable planets, but they haven't been followed up yet. They haven't confirmed them. You want to confirm them by going out and trying to measure the radial velocities and guarantee they're planets. So we know they're there, we just haven't gone back and proved it. So right now, the total number of planets is 5,500 basically, compared to 22 years ago, 0.
Well, when you say 5,500,
Yeah.
if that's a sample and you have the thought, what proportion of the universe are we talking about?
Oh, wow. Oh.
So what you're talking about, the 5,500
Yes.
is the near planets.
Those are the planets around nearby stars. Yeah.
Right, yeah.
You're talking about out to a distance of maybe a few hundred light
We
years.
don't know what the hell's
No,
going on.
that's right, exactly.
Way-
Right. The crucial point about this is, given the sample you're finding, they are so ubiquitous. They're everywhere.
Right.
Every star, within the limits of observability, has them. We can basically take that and extrapolate. And we now know the number of planets out there is going to be on the order of billions of them.
Right, probabilities.
Totally, exactly. Just scale it up.
Right.
Because you're only finding the ones you can find in your technique, which is still 1 in 100. And that's only the nearby ones in terms of planet being near to the star. So it's a very select sample, but still, there's so many of them, it's incredible. Here's a little, you can go online and watch this if you want. This is a little movie made in 2013, which shows all the planets discovered as of 2013, but it shows you the actual planets and their orbits around their stars. Timed to the right amount of time. The stars have been removed so you can actually see the planets. It's in order. Here we go. Put it on and I'll let it go. You'll see the move. There's a clock up here. That's the date. So each one, the time it changes, it's 1 day.
Oh my God.
So it's on the real scale.
Oh my God.
And you let it go.
Amazing.
And here we go. You can watch them go around in orbits.
Oh, my goodness.
Each one of those dots, no matter what color it is the planet, around a single star.
And you came up with that image on your own?
No. There's a guy who worked for Kepler, the mission, who put this together, and it gets updated about once every 2 years.
Is it online?
It's online. You can see it online. It's on YouTube.
How many of these planets that we even know are close to us are even reachable by us?
None of them.
None of
0.
Hundreds of
So,
planets.
them. And these are the close ones.
These are the close ones. Yeah.
Now, that
It's
means,
going to go in a second, so you
of
see.
course,
the-
you don't
the-
know if any of them could inhabit life.
No, I'm not saying that. No. I don't know if they can. My assumption is there's so many of them out there that some of them probably do. The question is, I just can't get to them. But I can study them now.
Yeah, but if you can't get to them, could any life on those planets get to us?
I hope not.
but they may have a better technology than
They might. That's the point. I hope not.
Well, yeah, but their condition, they can't get to us any faster than the speed of light, can they?
Well, I don't know what their technology is, you know. That's